All right, let's dive into a really fascinating puzzle today. How is it possible that the exact same element, carbon, can create both the hardest substance on Earth and the super soft, flaky stuff you find inside your pencil? It's a mystery that's hiding in plain sight, and believe me, the answer is all about atomic architecture.
Okay, let's really let this sink in. On one hand, you've got diamond. It's the hardest natural substance we know of. It can cut through pretty much anything. And then, on the other hand, you have graphite, right? The lead in your pencil. It's so soft and slippery that it just flakes away onto the paper with almost no pressure at all. I mean, they could not seem more different.
But here is the part that'll bake your noodle. They are chemically identical. Both of them are made of absolutely nothing but pure 100% carbon atoms, the exact same ingredient, but you get two completely wildly different results.
So this brings us right to the heart of our question for today. How on earth can the same element build both an unbreakable diamond and that soft, flaky graphite? Well, the answer isn't in what they're made of, but how they're put together. So let's get into it.
You see, the real secret here isn't in the what. It's not the carbon atoms themselves. It's all in the how. It comes down to their atomic blueprint, the way those atoms are arranged in something we call a giant molecular structure.
So what is that exactly? Well, a giant molecular structure is when all the atoms are interlinked in this huge repeating network, and they're held together by these incredibly strong connections called covalent bonds, which are kind of like the superglue of the atomic world. So don't think of it like individual little building blocks, think of it more like one single, massive, unified structure.
Okay, let's start with diamond. Its structure is the perfect example of something that is just built to last. It really is an atomic fortress.
So, inside a diamond, every single carbon atom is powerfully bonded to 4 other carbon atoms. This special formation is called a tetrahedral lattice, and it creates this perfectly rigid, interlocking 3D scaffolding that just extends out in every direction. There are no weak points at all.
And that atomic fortress is what gives diamond all its legendary properties. It takes a massive amount of energy to break those bonds, which is why it has such a ridiculously high melting point. It's unbelievably hard because all the atoms are locked rigidly in place, and because all the electrons are busy holding that structure together, there are none left over to run around and carry an electrical current, and that's why diamond is an insulator.
And here's a great example of that hardness in action. If you've ever wondered why a dentist's drill is so powerful, well, it's because it's tipped with tiny diamonds. Your tooth enamel is actually incredibly hard stuff, and diamond is one of the very few materials strong enough to actually grind it away. Wild, right?
Okay, now let's flip over to graphite, the other side of our carbon paradox. If diamond is an atomic fortress, you can think of graphite more like a skyscraper made of countless, loosely stacked sheets of paper.
So in graphite, the carbon atoms are arranged completely differently. They form these flat, two-dimensional sheets of linked hexagons. Now the bonds within each individual sheet are super strong, just like in diamond. But, and this is the absolute key to everything, the forces holding the different sheets together are very, very weak.
And because those layers are only weakly attracted to each other, they can just slide over one another with almost no effort. When you write with a pencil, what you're literally doing is shearing off thousands of these atomic layers and leaving a trail of them on the paper. This is what makes graphite feel slippery, and it's also why it's used as a great industrial lubricant.
But the surprises do not stop there. Remember how diamond won't conduct electricity at all? Well, get this. Graphite, its chemical twin, is an excellent conductor.
So what gives? Why the difference? Well, in graphite's layered structure, each carbon atom only bonds to 3 others. This leaves one little electron free on each atom. These spare electrons aren't locked into place. They can move freely between the layers, carrying an electrical charge just like the electrons in a metal wire.
Okay, let's just pause for a second and look at this summary. You can see it all laid out right here. It all comes down to the structure. Diamond's 3D lattice makes it extremely hard and an insulator. In total contrast, graphite's 2D layers make it soft and a conductor. It's all about the atomic arrangement.
Now, these different forms of the same element, they actually have a name. They're called allotropes. And this isn't just some weird quirk of carbon. This principle that the atomic structure defines the physical properties is a fundamental rule in chemistry. So let's meet one of carbon's close cousins.
This is silica. You probably know it as silicon dioxide. It's the main thing that makes up sand and quartz. And what do you know?
Its atoms, silicon and oxygen, are arranged in a rigid 3D lattice structure that's actually very, very similar to a diamond's.
And because its structure mimics a diamond, its properties do too. Just like diamond, silica is very hard and has an incredibly high melting point of over 1700 degrees Celsius. It's the exact same principle at work.
So, the ultimate takeaway from all of this is actually pretty simple, but it's also really profound. Atomic arrangement is everything. The way tiny invisible atoms are bonded together has a direct, powerful, and totally visible impact on the properties of the materials we use every single day.
It really makes you think, doesn't it? The next time you see the sparkle of a diamond, or even just use a simple pencil, you'll know the secret behind their powers. It's a powerful reminder that the world we see is shaped by an entire invisible world of atomic structures. Which leaves us with a final, fascinating question to chew on. What other everyday materials out there are hiding incredible superpowers in their atoms?